We want to bring up our next team, Wet Technik. Mark Musinguzi from, I didn't do that right at all, I apologize. Makerere University in Uganda.
Yes, sir.
So welcome to the stage.
Thank you.
How are you enjoying Grand Rapids so far?
Definitely, I'm enjoying it.
Great.
Yes.
Well, best of luck and take it away.
Okay. Where can I start from? Okay, let me take you guys to Uganda for a moment. Just like in the US, we have schools in Uganda. So I can't talk about schools without talking about the boarding system. Boarding system is where you spend most of your time at school. What do? Why? Because of academic time, and I think parents get tired of seeing you at home quite early in your life. So what happens? I can't talk about this also without talking about those times when we would wash our clothes. That's in the evening. And when the bell for supper goes, you just pour the water and literally just run away because you're going to miss supper. So that was wastewater. How we also interacted with this. This was the same school where there was so much water being wasted. There were water shortages also as well. So toilets would not be cleaned sometime. After a long day, you come, toilet dirty. So what we did, I and my colleague Dennis, right there, we bought from Club Funds, School Water and Sanitation Club, we bought big drums. That was in 2014, where we poured this water after use and hoped that when there's water shortage, at least the cleaners could use something so that we could have good toilets at the end of the day. So this was my first interaction with wastewater. Why am I telling you this? Because in Uganda, 75% of diseases are water-related, where we have around 2,600 students, or no, 2,600 kids dying from waterborne diseases. And eventually, when you add in industries which are polluting, our largest freshwater source, which is Lake Victoria, similar to the Lake Michigan here in size, we have so much effects that are following each other. So from this analysis, we were able to find out 60% of the composition of water was gray. Schools without proper wastewater systems were around 52%, and 1,628 boarding schools out of a potential 3,000. So over our PBL project, which we've been involved in over the last 6 months, we've had 2 case studies. What I want to bring to your notice here is Africa Hall, which is a hall in the university with around 800 female students, $408 per month spent on water. What's happening? This is 20% of the total budget, what they spend cumulatively. And as you can see towards the end of that, you're seeing poor waste disposal. This is a problem that's there, and from this microenvironment, this expands to being a general problem basically in Uganda. So second point, we went to Seta High School where the monthly expenditure is $850, but what was discovered here is livestock in the community was dying due to the large amount of wastes, 1,600 students. The water was not being handled well, so the water sources around were dying. That's the system behind, that's me in the picture. So what's happening? In all these settings, the linear economy is leading to water being taken to septic tanks and soak pits, where after it's taken to disposal. That's in households, schools, and slum communities. And factories, it's treated before disposal. So what we're proposing, a constructed wetland with improved aesthetics and reduced area requirements. Why? We need to properly collect this wastewater. That's what's coming, taken into the pre-treatment system, into the main filtration bed where there's a mixture of pumice and plastic bottle caps, modified and unmodified, and thereafter taken to the outlet. This is a representation of what our system would look like in a house or a school setting. So our materials, there's pumice, plastic bottle cap, and wetland flowers. Pumice, it's a natural volcanic rock, abundant but not being used that much. So what we want to do is further commercialize it, and it still carries out the filtration. The plastic bottle caps are abundant in the waste streams. We have already interacted with them, purchased them. That was during this PBL project. And we have chosen HDPE because it's less corrosive in contact with water as compared to PET and other types of plastic, and it's abundant. Then the wetland flowers, which improve the aesthetic appeal. So if you look at a household in Uganda of around 8 people, it takes 50 by 100-foot plot of land. It would need 10% of its land to be covered by the constructed wetland. That's large. When you go to a school with around 1,000 students, it needs 2,000 meters squared. This shows the volume of area requirements for this kind of system. So what we want to do is to reduce this by around 50%. through the use of this. So, of course, every product in the world has what it does for the buyer and the seller, what we're doing for the buyer. We have done a break-even cost analysis. Break-even meaning we have factored in the fixed costs and the variable costs in the total cost. Fixed cost being what someone is paying for the constructed wetland, variable cost, the maintenance over time, and the value we have gotten this by using the water availed for reuse that would have been gotten from the national grid. So this is coming up in place. And after 9 months, for the case study of Africa Whole, we found that after 9 months, they would have attained their value back, which is a relatively short payback time. So our key performance indicators are water quality, reduced water bill, proper water disposal, and improved aesthetics. Here we're looking at biochemical oxygen demand, which is the amount of organic matter present for schools, that is food remains from the washing of the plates. Phosphorus, which is present in the soap. Then aesthetics, we're trying to improve on that. So our solution is looking to maintain the efficiency, but reduce the area. The reduced water bill, we did the economic analysis from data we got from Africa Whole. We realized a 40% reduction in their water bill would be possible if the water is used for floor scrubbing and yard irrigation. This is a simple before and after peak of what's happening at Africa Whole. And these are some renders of what we are attaining to, what we want to achieve there, which we are starting on. So basically, to move people from their comfort zone, you have to give them some incentives. So what we're trying, low recycling cost. How? You do not need to treat to that high quality to perform different activities. The use of locally sourced materials, which we have interacted with, that's improving local content. The short supply chain, and eventually, because since there's less wastage, we're leading to an environmentally friendly solution. So this is our model we're trying to propose. So basically, the existing paradigm is wastewater is treated up to drinking water quality level and used in various applications that do not need this high quality. These applications, agriculture, toilets, floor scrubbing. So you can look in schools or households, the water does not need to be treated to that level, which is a bit expensive. So what we're trying to do is appreciate, yeah, we're not going to treat that level, but we are going to treat something that will have various applications. So what we've done over our entire project is from the start, we're able to pitch our idea at the PBL program, which is Makerere University in conjunction with Finland, and we have been given access to mentors from Finland and Uganda. Over this period, we have done workshops, trainings. It has been fun, but we've been able to, most importantly, create a detailed design, because over the last 6 months, we've been carrying out comprehensive wastewater treatment tests, lab tests, so that we truly understand the problem, and what we create at the end will be a true of what we want to actually achieve. So where do we go from here? What we want to do with the Wege Prize is we want to create a model pilot plant at the school, improve our expertise, test to provide the most low-cost solution, because that's what's going to attract people, and continuous research, with a total school reach of around 1,628 boarding types of schools. The market is there, but what you need is the right solution for them. So with the PBL program, we have done so much. And in addition to this, various SDGs we have met, such as SDG goal number 6, which is clean water and sanitation, but also goal number 12, which is responsible consumption and production. Responsible consumption is by reducing the amount of water used, and responsible production is the excessive use of water is basically reduced. So with help from this, we've been able to do this, and the National Planning Authority basically states the water use efficiency, water recycling, and water reuse will be key strategies to optimally use this resource. We want to take advantage of this in Uganda, and we believe we can be the next big thing. Thank you.
Thank you. Excellent job. I love how you tied that to the Uganda vision at the end, the purpose and the goal of the project. That's pretty important.
Yes, that's true.
So how did you, I was just curious, we're going to let the judges confer here for a couple minutes.
Okay.
So how did you select the case study schools that you worked with? They just schools that were nearby that you knew, or?
okay, Africa Hall is on our university. It's an on-campus. So all these pictures are at Makerere University. So you usually pass there when you're going for your lectures, and you see that state. It's not something nice to see on the university. So when we saw that, we knew this is something we can change. This is something that needs to change, most importantly.
I was wondered if it was because one of the schools was an all-girls school.
Yeah.
Is that, you know, let's face it, girls use more water than boys. That maybe that was one of your motivations on that?
I cannot comment on that.
You cannot comment on that. All right, I hear you. I hear you. Very smart, actually.
Yeah, but I guess it's all possible.
It's always possible.
Yeah.
So you're a musician, is that true?
Yeah, I play the organ in church. I played it from 13 up to now. Of course, I kind of stopped due to university, but yeah, if you have an organ, we can start.
All right, well, maybe for the judges forum in the morning, we'll have an organ there. All right, great. I think the judges are ready.
Okay,
Yeah, thank you for your presentation. That was really, really great. And I appreciated very much the context you gave to the innovation and what you're providing. I wanted to ask you about the certification potential of your water standards. So you mentioned that it's not potable, so it's not up to drinking water standard. But what is the level at which you are saying that that's good enough? And according to whom? Is there a standard that you're looking at for that?
Thank you for that question. There are WHO standards, Ugandan standards. So the parameters I gave you, such as biochemical oxygen demand, and others, such as pathogens, fecal coliforms, what you want to do is to treat to the efficiency, okay, to the treatment level, which is BOD of around 30 to 50, which can actually be used by people who are doing agriculture, and when they're using it, they actually won't get sick from using it because there's contact. But what we're treating is we don't want to treat up to one, okay, real drinking water BOD should not have, water should not have any BOD in it. So what we want is something right there, between 30 to 100 for BOD, which is the important parameter.
Okay, thank you.
And then I'd just like to add to that. So when this water is brought up to the certification, and when you're talking about using it in schools, I guess you're going to try to get this gray water into toilet use. Have you thought about the plumbing aspects of that?
Yes, for that, actually in the third month of our project, we went and toured some flats in Uganda. So we found that there's a specific place where people pour water from washing.
Okay.
And that water was directed to one septic tank. And another was directed, the black water from the toilet was directed there. So what we want to do is changing that system would not be hard because that's how buildings are constructed in Uganda. So that separation is already there. We want to take advantage of that. Then in addition to that, bringing it back would just need connection to before the cistern of the toilet, so that water is taken back into the toilet. So it would be, if the structure is not complex, because most of our schools are bungalows. They're not like high, like here. Most of them are low ground. So incorporation into the system would be quite easy.
Okay, great. Thank you.
It seems like you've done some prototyping across the whole solution. How much of the solution have you prototyped so far?
Okay, what we did is at Africa, we cleared the ground. So we were able to purchase pumice from people who deal in it, because most of it was lying on the ground. It was basically useless. So also we did that. Then we did the lab tests where we actually found that the biochemical oxygen demand was too high from Africa Whole. So that led to a setback of 1 month. Our mentors gave us a reading assignment, and we looked into anaerobic buffered reactors, which is a whole new kind of system. So we have now designed that because we realized a normal pretreatment system could not work there. So we went into that design, developed CAD models, ran some simulations, and right now, actually, the university has given us the chance to do our internship on the side. So that's what we're going to do for the next 3 months.
Okay. Thank you.
You're proposing a 40% reduction in the water bill, and you had said that you could achieve that percentage if water was used for irrigation, floor scrubbing, and toilets. How much water today, out of that $850 per month, is used toward things like irrigation?
Okay, so irrigation, basically, the university is green. So what's done is they water twice a day. So also, in addition to that, toilet flushing. It has 800 students, but what's actually on campus is some people stay off. So during the day, you can find like 1,200 girls who have come because the lectures are like, you have that lunch break, so you can't go back home. So they end up using those toilets. So you have so much water being used there by not people actually staying there. So we want to, most of the applications actually from some research by one of our doctors at the university found out that 60% of this water is black. That's used in toilets, that's used in activities like bathing and stuff like that. That cannot be recycled. But what we want to use it in is toilets, irrigation, and floor scrubbing. Because floor scrubbing, like Africa has 6 blocks, each has 3 floors. So you find on those 3 floors, they scrub them morning, evening. So all that water, why does it have to be like from the tap, like that expensive?
Got it. And so 40% of the water then is gray water, 60% is black water. Have you looked at living machines that have been used in other places to treat black water as well?
Yes, of course, black water, due to the high biochemical oxygen demand, we are looking at that as it needs actually technologies such as advanced membrane bioreactors, stuff like that, which is more technical, requires less space, but the quality issue. People in Uganda, there's no wastewater actually recycling. So people, when they see, oh, water that's from the toilet, you want me to water? It's a mindset, it would be a big problem.
Thank you. Colin asks, I love the idea and really enjoyed the presentation. I heard you say that you want to trial this with one school first and then learn lessons. This question might come too early, but what can you tell us about the scalability of the idea?
Okay, so what we want to do is people in Uganda believe by seeing. So when one school sees in another school, this thing is being done, and we want to carry out tests. You know, when you have results, you show that this water was achieved after, because there's that startup period for the system to take up. So when you see after this time that the system is actually working, you go with those facts in a paper, you go to another school, to someone else, and tell them, okay, hey, this has worked here. That school can tell you it has worked. And from there, I believe we can go places. The 1,628 schools, of course, we can't reach all of them, but having 12 of these a year would be great for start.
That's great. Oh, and then I guess I'd like to add to that. So what is the size of the average school? Like, so when you're talking about scalability and whatnot, how big, like, what would you be comfortable with, I would say?
The
starting?
school size or the?
Yeah, the size of the school.
Okay, since most of the schools are not urban, they are sort of rural.
Yeah.
So there's a lot of land. They have land. That's the good thing with schools.
Right.
So putting that solution there would not be that hard. And with our reduced area requirements, which we have to attain through the research, it can fit anywhere.
Okay.
I have a 2-part question. One is that how long do your systems last? Is there anything
Okay.
that needs to be renewed in the system?
Yes, yes.
And the second part is a little bit different, but it's you mentioned that your solution is coming in to reduce land use. So there's existing solutions that could be that are managed wetland or managed. I can't remember the word. Constructed wetlands. Are there any benefits that are currently like? Why is that solution very widespread in terms of actually effectively managing wastewater, or is it really just the land use that you're adding value to, or is there some problem with that solution as it's currently being developed?
Okay, for the first question. Okay, no, for the second question. Basically, we're looking at, in Uganda, there's nothing like green. We're trying to change to green because there's green everywhere. So when you add aesthetics to these flowers, it didn't look like a wastewater treatment system. We're trying to spark that thing of, oh, I would like to have this in my compound, not that I need to recycle the wastewater. I just need to have this in my compound because I guess that I'll have something. When my friends come over, I say, can you imagine what this is? This is wastewater. The water comes out here, it waters here. What? So we're trying to make it, it's like a new thing. People don't really think of green solutions, environmentally friendly, because there's no pollution there. It's minimal industrially, but it's not like a major kind of thing that, oh, there's no green space here. There's green space. You should all come to Uganda.
And about the life cycle, so like
life
if
cycle,
you need
yes.
to renew any aspect
Okay,
of
so
your system.
pumice and bottle caps. What happens is when you realize the efficiencies or the treatment efficiency, the water coming out has reduced in standard, then what happens for normal wetlands is you all remove the gravel, because they use gravel, you wash it and put it back, because it's just that it has been clogged. So for ours also, it's a similar system where you uproot and you remove and just wash and put back. So it's sort of hard, of course, digging up the whole thing, but it's better because you can just put them back and you continue working. Then the pumice, after a long period of time, let's say like 10 years, it has become so soft, so you can just use it agriculture because most of the nutrients, wastewater is nutrient rich, most of these nutrients have entered the pumice. It softens, you can give it out to people.
Colin has a follow-up. While you have reduced the space required compared to a typical wetland, the space demands are still considerable. How will you sell this idea to schools, companies, and households?
Okay, first of all, we want to start with the aesthetics that I've explained, because it's a new thing, people may get excited. Then, in addition to that, is this water, when you look at other wastewater treatment systems, that stuff is like 300 million shillings, which is around $100,000. So you can't have that on my compound in a school. So this is actually, it has proven to be the cheapest solution to wastewater recycling. But making people actually want it, it's because of the aesthetics. And the value, you show the payback time. People, okay, it depends on the price of water. Like in Japan, water, 1 unit, which is around 1,000 liters, is $4. In Uganda, it's $1. In America, so it's $1. So based on the water cost where you are, some people, it may not be $1. They have a borehole. So they go and fetch from the borehole, maybe like 25 miles away. That all those factors come into play, and you would find that actually reusing this water for irrigation, for all these activities would be beautiful.
Thank you.
Nice job, Mark. Congratulations.